Bending and stretching. The first thing that you have to know is that you can either apply forces on an object in order to make it bend, you can either apply forces on an object to stretch the object, or you can compress the object, okay? So bending, I think everybody knows what bending is, bend an object. Stretching it will be to try and pull it out. Things like springs, rubber bands, for example, they will stretch. And compressing is if you put the forces in opposite directions on the object and you try and squash the object. What you have to know about bending, stretching and compressing is that it requires at least two forces. You cannot bend an object with one force. So if I hold the ruler and I try and bend it with just one arm, it's not going to bend. Yeah? I have to apply two forces on either end and therefore I can bend it. If I want to stretch this object, I cannot just stretch this object by pulling it, not going to stretch. Alright? Two forces either myself, or I could tie it to a fixed surface and I could stretch it against that. Alright? So there are still two forces. For example, if I tie it to the wall, then the wall will pull it as I pull it as well. Alright? Two forces. And again, compressing. I either myself apply two forces on either end and I squash it myself, or I put it on a surface and I apply the force at the top down. The table is obviously applying a force upwards. So again, there's always going to be two forces if you want to bend, stretch, or compress. Okay? Elastic deformation and inelastic deformation. Okay? Elastic deformation, you need the definition, which is if you apply a force on an object, alright, and the best example of this is a spring. I don't actually have a spring with me, but if you apply a stretching force, for example, or a compressive force on a spring, or even if you bend the spring slightly, okay, it will deform. Now, deformation in general, people think, oh, if it's deformed, then it's broken. Yeah? So deforming, in general, people think it's not a good thing. Alright, if I deform this, oh, you've broken this, or you've ruined it. It's not the case. If it elastically deforms, so if I stretch the spring, and I let go, and I remove those stretching forces that I'm applying, then the spring will go back to its original shape. Yeah, 9 times out of 10, if I stretch a spring and let go, it goes back to normal. That's elastic deformation. So the definition of elastic deformation is if you apply a force on an object to stretch, bend, or compress, when you remove the force, it will go back to its original shape. Okay? So that's elastic deformation. So yes, I'm still deforming this ruler. That's a deformed ruler. Yeah? But if I let go, it goes back to its original shape. So I've elastically deformed it here. Alright? So when you remove the forces, 2 marks, even in year 12 physics actually, in the A-level exam, 2 marks, define elastic deformation. When you remove the forces on an object, it returns to its original shape. Okay? So it's the same for this. Inelastic is the exact opposite. If I inelastically deform something, I'm going to deform it by bending in this case. Okay? If I bend the ruler too much, then eventually this ruler will snap. Alright? There's no way if I let go then when it's snapped that it's going to be the same ruler as it was before. Okay? For springs, if you stretch a spring, I'm sure you've all done this at some point, when you get one of the little metal springs, and if you stretch it too far and you let go, you just have a very long spring that doesn't go back to its original shape. So the definition of inelastic deformation is if you remove the forces on the object, it will not return to its original shape. Okay? That's inelastic deformation versus elastic deformation. And you need those two definitions. Okay? Then we move on to force extension. So if you start with a spring, just a normal spring, no weight on it, you apply no forces to it, you just hold the spring from the top, okay? Then you're going to have an original length. A spring will have an original length generally about that long, okay, L. So here's the spring in its original shape. If I apply a force, so in general what we do with springs, and we're going to do this in the core practical, is if you hang the spring from the top, say on a clamp stand on a clamp, and then you hang a weight off the bottom of the spring, it's going to extend from its original length down to here, let's say for example, depending on the force which is due to the hanging masses that you add. Okay? The force that you apply, if you're applying it vertically, is the weight. So if you're adding 10 gram masses and you add 3 10 gram masses, then you times that by gravity 10, and there's the force, which is the weight in this case. Okay? This is your extension. You need to be very careful that obviously when we answer questions, you remember that there is an original length, so the extension is only this. Questions could be, the original length of the spring is 0.1 meter, 10 centimeters long, and then you apply a force mg, and the new spring comes down to here. The new length of the spring is 0.2 meters, for example, so it's doubled in length, okay? What's the extension of the spring? The extension is only 10 centimeters, okay? A few times people will say, right, oh, the new length is 20, this is the new spring, so the extension is 20 centimeters, all right? It's not. Just make sure you subtract the original length, or you bear in mind that the extension is only the change, okay? Because if I add one more plate here, and therefore I increase the force by another 10 grams times gravity, then it will go down a little bit more. Again, the extension is only going to be the change from the previous point. It's not then, the extension in the second case is not all the extension from before and then the extra. The extension, if I add another 10 gram mass, is only the change from the last point it was at, okay? So you have original length, which is obviously the same for every object, and then the extension is what is its change every time I add another force. Okay, and in general, when we do that vertically, the force that I add is going to be the masses times by the gravity if it's vertically and it's going down. Okay? What we do with that then, if we created a table and we had the force that we were adding and then the extension that we were measuring, we can draw a graph of force extension. And for springs, it turns out that the graph that you produce is a directly proportional relationship. So you have a straight line. It goes through 0, 0, that means it's directly proportional, okay? Those are the two conditions. It has to be a straight line, and it should go through 0, 0, okay, for it to be directly proportional. That means for springs, if I double the force that I add to a spring, then I will double its extension, okay? So that's the relationship. If we want to write that in an equation, which is the next part, but just for now, if I say the force is directly proportional to the extension of the spring, then I can create an equation, F, change the proportionality to equals K times X. And in fact, this time, the constant of proportionality for this equation stays as K. In general, in other equations, we change it for one that obviously makes sense for the context or the physics. This one, we keep it like that, and I'll tell you what K means in 15b. Okay? So force extension graph, if the graph is a straight line through 0, 0, which for a spring it should be, for the most part, then you know force is directly proportional to extension, and there's your relationship there. Okay? Very careful. If I plot the graph force against length, then it is not going to start at 0, 0, because the original length of any object is not 0. You can't have no length for an object. Okay? The spring at least has a little bit of length. Okay? So if you plot a graph, or if in the exam they give you an axis which is force and length, you have to be very careful that it doesn't start at 0, it will start somewhere over here. Alright, so it's not quite the same as force extension, and it doesn't pass through 0, 0, so it starts at the original length, and then you have force applied extension for this section here. Okay? This part, the two parts of the graph that are most important are, is the graph a linear relationship? In this case, yes it is. The whole graph in this one is linear. That means it's directly proportional, we know that. Okay? If plotted against the extension. This section of the force length is linear. So this section is linear, but it doesn't go through 0, 0. Okay? But if you stretch a spring, like we said, if you go too far, if you apply too great a force, then you're going to inelastically deform your spring. So if then I let go, it wouldn't go back to its original shape. So here, if you see the graph past a certain point it becomes non-linear, then the spring has been stretched too far. Okay? So in this entire section here, it's linear, it's directly proportional, then the spring will go back, it's elastically deformed, it does go back to its original shape. Past a certain point, there is a very small section where it is still elastic, where it's not linear. Okay, you don't need to worry about that too much at this point. But if you go past a certain point, which we call the limit of proportionality, so past this stage, there is no more direct proportion, then it's non-linear and it's been stretched too far. Okay, will not return to its original shape. Other examples of non-linear relationships for stretching and compressing, for example, is the rubber band or elastic band. So for example, if you plot a graph of force and extension for a rubber band, you will get a non-linear relationship for the entire trend. Okay? There is no situation if you're stretching a rubber band where the force would be directly proportional to its extension. It doesn't work like a spring. It's slightly different. So the curve that you get goes up here, goes over there, comes down here, it's quite flat there, then it goes up again. If you're asked to describe the relationship between force and extension for a rubber band, or any graph they give you, which is non-linear the whole time, then you can have a look here. You're applying a lot of force in the first place, and you're getting very little extension. That's quite a stiff material. If I have to put a lot of force on this object, and it's not really stretching, then it's quite a stiff material. Then you get past a certain point, and actually only a little force will take quite a lot of extension. So in this point, you can kind of assume that, okay, it's kind of lost its bonds between the molecules inside, and it's really stretching, I don't even have to pull it, and then it changes again. So rubber bands are very complex, not nearly as simple as springs. Okay? So linear directly proportional, if plotted against extension. Non-linear, stretch too far for a spring, which is this section. So this is the only section for the spring which is non-linear. And rubber bands throughout the whole graph is non-linear.